Hey guys, welcome to episode 13, lucky number 13, the first one of the neurology module. Thank God Almighty psychiatry's over. Amen, amen. So, just a few announcements. Number one, remember if you can't see the video for some reason, and if it's blurry for some reason, feel free to check out the handout found in the video description at the bottom of the video on YouTube. Number two, always feel free to subscribe. You get notifications when I upload new videos. Number three, just a shout out to Phi Dex Fest, which is PDC's annual fall fundraiser for St. Jude's Research Hospital, which provides free treatment for families and their kids undergoing treatment for their serious diseases. It's a good cause. Phi Dex Fest is on Saturday, October 13th at 6 p.m. at On the Rocks, within walking distance in case you want to drink. Please don't drink and drive, that's bad. Also, it's illegal in Virginia and all across the United States. There will be all-you-can-eat food for $15. It's all you can eat. You get all you can eat veggie trays, cheese trays, meatballs, chicken salad wraps, Caesar wraps, brownie trays, chips and salsa, pretzel bites, chicken tenders, burgers, fries, and the like. You also get karaoke. You might hear me and the other Christians sing that night if you want to come out. There's speed bingo and raffles. Also, there's $3 rails and $3 domestic beers. Pay at the door or pay ahead. See someone from PDC for more information. Lots of good time, good food, good people. Come out and have fun and raise money for St. Jude's Research Hospital. All the money goes to St. Jude's. So let's get started. Okay, so the first class of drugs we're going to talk about are your drugs for multiple sclerosis. So basically, multiple sclerosis is a disease characterized by the infiltration of reactive T cells into the CNS, which causes damage to the myelin sheath. So your first class of drugs we're going to talk about are your interferon betas. So these are cytokines or proteins that are involved in anti-inflammatory responses, and interferon beta also improves the blood-brain barrier integrity to resist T-cell infiltration. So interferon beta has two mechanisms of action. It is an anti-inflammatory agent, and it improves the blood-brain barrier integrity, which resists T-cell infiltration, therefore resisting damage to the myelin sheath caused by T-cell infiltration into the CNS. So there are two types of interferon beta. There is 1A and 1B. So 1A is glycosylated, meaning it has sugar groups attached, and it has the same amino acid sequence as endogenous interferon. In contrast, 1B is not glycosylated, and it does not have the same amino acid sequence. Specifically, it has deletion of methionine 1. So it has deletion of methionine 1 in part of the sequence, and it has another mutation within the sequence that Dr. Zhang didn't specify. Let's see. Yeah. So, next class of drugs are your monoclonal antibodies. So these form molecular interactions with alpha 4B1 integrin expressed by inflammatory cells. Therefore, by forming molecular interactions with these receptors, they block the invasion of immune cells into the CNS, because the immune cells bind to the CNS by these receptors, and by this receptor alpha 4B1 integrin binding to the blood-brain barrier, it allows the immune cells to go into the CNS and invade the CNS, and therefore degrade myelin. So, alpha 4B1 integrin is important for our immune cells to attach to the blood-brain barrier, and the blood-brain barrier allows the immune cells to invade or cross through the blood-brain barrier, and therefore damaging the myelin sheaths. These have a possible drug-drug interaction with other immune-modulating drugs because these themselves are immune-modulating drugs. And if you haven't noticed already, monoclonal antibodies you can find them in the name of the drug by the suffix mab. So adalimumab, Humira is a monoclonal antibody. Alemtuzumab, daclizumab, rituximab, acrelizumab are monoclonal antibodies, because M AAAB is the long form of monoclonal antibody. Okay, so I drew out the mechanisms for you in picture form because I love pictures. So these are your this is your lymphocyte and this is your B cell. So alemtuzumab and daclizumab attach onto the lymphocytes, whereas rituximab and ocrelizumab attach onto the B cells. Specifically, alemtuzumab attaches onto surface antigen CD52 of the lymphocytes, whereas daclizumab attaches onto interleukin 2 receptor CD25 onto the lymphocyte. On the B cell, both rituximab and ocrelizumab attach onto surface antigen CD20 on the B cell. I think that's it. So yeah, by these drugs, alemtuzumab, daclizumab, rituximab, or ocrelizumab, attaching onto these different receptors and surface antigens, they block the immune cells from invading the CNS because these receptors cannot attach onto the blood-brain barrier anymore. Next drug, glatiramer acetate. This is a polymer of lysine, tyrosine, glutamate, glutamic acid, glutamate, same thing, and alanine. It turns out that these four amino acids are components of the myelin basic protein. So by having a substance that looks like myelin basic protein, you can have two mechanisms of action. Number one, you can induce tolerance of the system to the immune response, similar to vaccines. So vaccines are basically dead viruses or whatever, and you put these dead viruses into your body, and your body induces tolerance. In the same way, by putting something that looks like myelin into your body, you can induce tolerance of your system to the immune response. Number two, mechanism of action. It can act as a decoy for immune responses. So the immune cells target this drug rather than the actual myelin sheath, and therefore you can block the destruction of the myelin sheath. Easy way to remember these amino acids in this drug. You have GLAT, GLAT. So glatiramer is composed of glutamate, alanine, glutamate L, lysine A, alanine T, tyrosine. So the first four letters of each amino acid are found in the first four letters of the drug. Easy way to remember it. Mitoxantrone. This one's pretty cool. So it's a type 2 topoisomerase inhibitor. Meaning that it inhibits the cutting of both DNA strands. So type 2 topoisomerase cuts both DNA strands to relieve supercoiling. So this allows the DNA to replicate and synthesize. So what mitoxantrone does, it inhibits type 2 topoisomerase, meaning you can't cut both DNA strands to relieve supercoiling. Therefore, the DNA cannot replicate, and synthesize correctly. Also repair. So, how does it do this? Let's see. By intercalating or alkylating DNA purine bases. So, this is the structure of mitoxantrone. This is the scaffold. And these are actually the reactive units. So, this hydroxyl and this hydroxyl. So, let's see. What mitoxantrone, you don't have to know the mechanism, but pretty much know where it reacts. So, it reacts over here and over here. How it does that, how it intercalates DNA purine bases, which I think is pretty cool. Let's see. So here's your scaffold. Here's your arm. There's your arms. So basically what happens is the oxygen group leaves, and this nitrogen forms a cycle. This forms a cycle, oxygen leaves. So what happens is... let's see, 1, 2, 3. You form a aziridine ring. And if you haven't blocked it out of your memory yet, if you remember from baby medchem or P1 medchem, 3-membered heterocycle rings are very reactive. So this nitrogen ring is very reactive. So what it does is once you find once it finds DNA, it's too strong. Oh, whatever, don't care. It actually forms a bond. The electrons form a bond with DNA, and here's your scaffold. There you go. So, what mitoxantrone does is it forms bonds with DNA through this heterocycle Azerian ring, which is very active. And by doing so, DNA cannot, you can't relieve supercoiling. So, and the type 2 topoisomerase enzyme cannot fit into here anymore, into the DNA anymore to cut the strands and relieve supercoiling, because the mitoxantrone is in the way, because it forms a bond with DNA. So pretty cool, right? It's not, well, I'm just geeking out. Dimethyl fumarate mechanism of action. It depletes glutathione and induces induction. It induces anti-inflammatory stress protein HO1. So it depletes glutathione and it causes the release of anti-inflammatory stress protein HO1, which is released when lymphocytes attack the myelin sheath. Fingolimod. This is also another cool mechanism of action. It's a sphingosine 1-phosphate receptor modulator. So at the receptor level, it functions as an agonist, but at the functional level, it functions as an antagonist. Meaning that, so at the receptor level, it activates the G protein coupled receptor, the sphingosine 1-phosphate receptor. So at the receptor level, it acts as an agonist, meaning it activates this GPCR, or it activates sphingosine 1-phosphate receptor modulator. However, at the functional level, it acts as an antagonist, meaning it stops production. It stops the immune response, and, well, it stops the autoimmune response of the lymphocytes invading the CNS and therefore attacking the myelin sheath. So, at the receptor level, it functions as an agonist by activating the sphingosine 1-phosphate receptor modulator, but at the functional level, it acts as an antagonist by preventing the lymphocytes from invading the CNS and attacking myelin sheaths. Let's see. So here's the structure of fingolimod. Let's see. So here is the structure of fingolimod, and it acts on the sphingosine 1-phosphate receptor because it actually looks like sphingosine. So if you compare fingolimod and sphingosine, they actually look the same. So they have a long alkyl chain with a double bond moiety, a nitrogen or an amide, hydroxyl, another hydroxyl. So in order for, let's see, so in order for fingolimod to work, it has to be, so okay, back up. So in order for sphingosine to work on, the sphingosine 1-phosphate receptor, it has to be phosphorylated to form sphingosine 1-phosphate. Because the sphingosine 1-phosphate receptor needs sphingosine 1-phosphate. So sphingosine is converted to sphingosine 1-phosphate by just the conversion of this hydroxyl to a phosphate. So everything's staying the same in both sphingosine and sphingosine 1-phosphate. The only thing that happens to sphingosine is phosphorylated at this hydroxyl to form a phosphate group. So in the same way, for fingolimod to work on the sphingosine phosphate 1 receptor, it has to be converted from this hydroxyl to a phosphate group by a kinase in order to work. So in order for fingolimod to work on the sphingosine phosphate 1 receptor, it has to be phosphorylated first by a kinase in order to act on that phosphate receptor. So yeah, I told you earlier, but this, let's see. So specifically the mechanism of action is it migrates lymphocytes in lymph nodes and prevents them from the autoimmune response of attacking myelin sheath in the CNS. So, recap of fingolimod. Oh, you can remember this easily as a sphingosine 1 receptor modulator because Fing actually has the same root as Fing, or sphingosine actually sounds like fingolimod. Fingolimod. Anyways, recap of fingolimod. So, it acts as a at the receptor level. It acts as the agonist at the sphingosine 1 receptor. However, it ultimately functions as an antagonist by blocking the function of lymphocytes in the CNS. So specifically, it migrates lymphocytes into lymph nodes and prevents them from the autoimmune response in the CNS. Fingolimod has to be first phosphorylated by a kinase in order to act on the sphingosine 1 phosphate receptor. Because in order for sphingosine, which fingolimod is based off, to work on the sphingosine 1 phosphate receptor, it has to be phosphorylated first. So in order for fingolimod, which looks like sphingosine, to work, it has to be phosphorylated by a kinase in order to act on the sphingosine 1 phosphate receptor. Teriflunomide. Mechanism of action, it inhibits pyrimidine synthesis by inhibiting dihydroorotate, therefore inhibiting T cell growth. So next class of drugs are your skeletal muscle relaxants, which include mefenacin, which is a glycerol derivative. So glycerols, if you look at the structure down below, have 3 carbon attached to 3 hydroxyl groups. So 3 carbon 3 hydroxyl groups are glycerols. So mefenacin is a glycerol derivative that forms ether bonds at the hydroxyl group. It's selected for the spinal cord. It's a prototype for your other skeletal muscle relaxants, and it has many side effects. However, in contrast, the next 3 drugs are more selective for the spinal cord and has less other side effects, sedation effects. Pharmacologically, they're sedatives or hypnotics. So you can tell the difference between your prototype and your more selective spinal cord and skeletal muscle relaxants in that mefenacin is just a simple 3 carbon 3 hydroxyl unit. However, your more selective agents, chlorphenicin, methylcarbamol, and carisoprodol, have more complicated structures. So they actually have the carbamate. So they're not just 3 simple carbon hydroxyl units. This hydroxyl at the top is replaced by an O double bond O NH2, which is a carbamate. So your mefenacin, which is your prototype, does not have the O double bond O and H2 at the top, whereas your more selective spinal cord agents have the O double bond O and H2 at the top. Let's see. And y'all know from Psyche, if you haven't blocked it out from your memory yet, benzodiazepines are agonists at the benzodiazepine receptor on GABA A, which is a ligand-gated ion channel for chlorine. And specifically, it acts as a positive allosteric modulator. Your GABA receptor agonist, which is baclofen, it's a GABA analog, and you can tell it's a GABA analog because it looks like GABA. So here's the gamma analog. So GABA actually stands for gamma amino butyric acid. So easy way to remember that is here's your amino group, here's your amino group, and here's your acid group. Here's your acid group. So baclofen actually looks like GABA because it has your amino and your acid group. High dantoin derivatives, dantrolene, binds to the calcium channel proteins, which regulates membrane potentials. Because if you remember that if you break down the myelin sheath, you disrupt the membrane potential, and which leads to muscle spasms, numbness, weakness, loss of vision, double vision, anything involved in CNS relaying of information through neurons. By binding the calcium channel proteins, they regulate membrane potentials after your lymphocytes and your other T cells demyelinate and disrupt the membrane potential. You can easily remember this because dantrolene is a high dantoin derivative. Okay, so now we're going to talk about Alzheimer's disease. So this disease, the pathophysiology of this disease is based on the cholinergic hypothesis, where Alzheimer's disease is caused by the disruption of acetylcholine in the body. So it makes sense to have drugs that act as acetylcholinesterase inhibitors. You can also have NMDA antagonists, since NMDA is an excitatory receptor that works via glutamate, which is the excitatory neurotransmitter. So specifically, acetylcholinesterase is the protein or enzyme that catalyzes the breakdown of acetylcholine into acetic acid into choline. So acetylcholinesterase is an enzyme that breaks down acetylcholine into acetic acid and choline. So acetylcholinesterase inhibitors block the conversion or the breakdown of acetylcholine into acetic acid and choline, therefore blocking the disruption of acetylcholine levels in the body, therefore managing the symptoms of Alzheimer's disease. So you have 3 different drugs that act as acetylcholinesterase inhibitors. You have tacrine, donepezil, and rivastigmine. So tacrine is a type 1 acetylcholinesterase inhibitor, meaning it sits right on the acetylcholine binding site. Donepezil sits on the allosteric site, which changes the conformation of the acetylcholinesterase enzyme, therefore decreasing enzyme activity. Rivastigmine is a type 2 acetylcholinesterase inhibitor, which forms covalent bonds with the enzyme. So whereas tacrine is a type 1 inhibitor, meaning it sits on the active site, rivastigmine is a type 2 inhibitor, which means it actually forms the bond with the enzyme, therefore stopping their enzyme activity. So tacrine works by sitting on the acetylcholine binding site, therefore it blocks acetylcholine coming into the binding site, and therefore you can't break down acetylcholine. Whereas rivastigmine actually forms a bond with acetylcholinesterase, therefore acetylcholinesterase can't break down acetylcholine by forming bonds with acetylcholine. By forming bonds with rivastigmine, esterase cannot form bonds with acetylcholine, therefore it cannot break down acetylcholine into acetic acid and choline. Whereas donepezil sits on the allosteric site and blocks the conversion of acetylcholine into acetic acid and choline. Galantamine is a natural acetylcholinesterase inhibitor that acts as a competitive and reversible inhibitor. Your NMDA receptor antagonist is memantine, which blocks glutamatergic system. Remember that glutamate is the excitatory neurotransmitter involved with NMDA, so memantine blocks NMDA, therefore blocks glutamate activity. NMDA is endogenously a selective agonist at NMDA receptor, which makes sense because the NMDA receptor is named after NMDA, which is the agonist for the receptor. Your herbs and natural products, you have ginkgolide, ginkatin, bilobalide, huperzin A, curcumin, resveratrol, I'll let you figure out how I'm going to memorize that. So, Alzheimer's can also be thought of as being formed by different disruption of the CNS by the formation of different plaques. So you can form plaques in two ways, the tau proteins or amyloid beta. So tau proteins bind to microtubules, and phosphorylating tau proteins detaches them from the microtubules and allows them to self-aggregate, leading to neuronal death. Another way you can form plaques is by amyloid beta. So amyloid beta also forms plaques, which also leads to neuronal death. So how does it do this? So here's your amyloid precursor protein, which spans the membrane and actually protrudes from the membrane. So beta secretase cuts at the above the membrane or extracellularly, and gamma secretase cuts intracellularly or below the membrane. This leads to formation of a little amyloid beta inside the membrane, and it's actually small enough to slip through and actually aggregate with other amyloid betas from beta secretase and gamma secretase cutting other APPs or amyloid precursor proteins, and this allows the multiple amyloid betas to aggregate or form plaques. So cutting amyloid precursor protein APP, which is not small enough to leave the membrane, allows it to be small enough to leave the membrane and aggregate and form plaques, leading to neuronal death. Therefore, it makes sense to have drugs that target beta secretase through BACE, base, and mimapsin 2, to target gamma secretase, and to target amyloid beta cells. By removal of the amyloid beta plaques, inhibition of aggregation, or the technical term is oligomerization, which is a technical term for aggregation, and degradation of amyloid beta. Diagnostic agents to detect Alzheimer's disease include Pittsburgh compound B, florbetapir, and florbetapen. You can tell these are diagnostic agents because if you know anything about radiology, you know that isotopes are used to diagnose or to form pictures on your diagnostic images. So isotopes are denoted by numbers in front of atoms. So 11 CH3, 18 fluorine, fluorine 18. I was too lazy to draw structures, but if he gives you a structure for some reason and gives you and they have 11 or numbers in front of the atoms, for example 11 CH3, 18 fluorine or 18 fluorine, then you know it's an isotope, meaning it's used to radio label different compounds. Therefore, it's used as a diagnostic agent, so you can see stuff light up on your MRI or CT screen. Okay, so before I get started with the Parkinson's Disease agents, just wanted to give a shout out to Wiley and her dog Cosette. Wiley's probably the biggest fan of these videos, so it's only fitting she gets the first request shout out. So here's her dog Cosette. I love Cosette, and here's a video of her.
Hey, what's up, fam? It's the famous Cosette! Oh, man! Hi, girl! What's up? What?
Oh, isn't she cute? Anyways, if you want to follow Wiley and her dog Cosette on Snapchat, feel free to do so at CASESENSBON. That's her Snapchat name. Again, it's Casonsbon. I don't know how you pronounce it. I don't know, I didn't ask her. Anyways, feel free to follow Cosette. That's her Snapchat. Okay, so before I start the last section, Parkinson's disease, just wanted to remind you that if you have a shout out for yourself, a significant other, or to one of your pets, feel free to let me know. I already got another request coming in for the next episode, so look out for that. Okay, so Parkinson's disease. Basically, it's caused by a deficiency in striatal dopamine. So, this is one of the objectives. You have to know the dopamine biosynthesis. Dopamine biosynthesis. Let's see. So dopamine starts out by tyrosine. So tyrosine is the amino acid that starts dopamine synthesis over here. This is tyrosine. So first off, tyrosine hydroxylase adds hydroxyl group at the 3 position. So here's the 3 position. It adds it over here to form this compound by tyrosine hydroxylase. Then the decarboxylase is going to come in and remove this carboxyl group and form dopamine. Notice how dopamine has no carboxyl group. In the name, it's called dopamine, dope carboxyl group. It's called dopamine. So here's your free amine. That gives you a hint on what the product is. So tyrosine is converted this compound first by tyrosine hydroxylase, which adds hydroxyl at the 3 position. Then T-carboxylase is going to remove the carboxyl group to form dopamine. So hydroxylate, then decarboxylate. Hydroxylate, decarboxylate. I made up a song for you. Okay, so you also have to know metabolism of dopamine according to the objectives. So let's see. Okay, so you start off with dopamine. There's 2 pathways. There's your monoamine oxidase and your catechol O-methyltransferase, or COMT. If you remember anything from psych, if you didn't block it out from your memory again, remember that MAO forms an acid and an alcohol. So you already know your 2 products from MAO oxidation of dopamine. You have an acid and an alcohol. In the middle, the intermediate is dopamine is an aldehyde. So before you convert it to an acid and an alcohol, you have to first convert it to an aldehyde. So over here, dopamine is converted to an aldehyde, or dope aldehyde by MAO. Then it's converted to an alcohol by alcohol dehydrogenase, and it's converted to the acid by aldehyde dehydrogenase. So MAO converts it to the aldehyde to dope al, which is converted to the alcohol by alcohol dehydrogenase, or dope et. So et refers to ethanol. So your 1,2 ethyl group, and your alcohol is an ethanol. Dope aldehyde is also converted to the acid by aldehyde dehydrogenase. Now, what's your secondary pathway? Catechol O-methyltransferase. So catechol O-methyltransferase, in the name, it transfers an O-methyl group onto the compound. So here's your O-methyl group at the 3 position. So all the action happens at the 3 position. So dopamine is converted to this 3-methoxytyramine by catechol O-methyltransferase, which adds a O-methyl at the 3 position. Now you're gonna add MAO. You know that MAO converts things to acids and alcohols, first by converting them to aldehydes. So here's MOP-al, the aldehyde version of 3-methoxytyramine. Now, instead of doing alcohol dehydrogenase, you're going to do aldehyde dehydrogenase. And remember, aldehyde dehydrogenase converts it into what? An acid or an alcohol? The alcohol. Acid, my bad, acid. Awkward. Okay, so, alcohol dehydrogenase, aldehyde dehydrogenase converts the MOP-al into the acid, which is shown here. So in the MAO pathway, you can get to HVA, which is the final product, by aldehyde, alcohol, the acid by aldehyde dehydrogenase, and this dope AC, which is the acetic acid. It's called acetic acid because it has 2 carbons. Acetic acid is 2-carbon acid. So dope al is converted to dope ac by aldehyde dehydrogenase. Then dope ac can be converted to the final compound, HVA, by catechol methyltransferase. Because if you compare dope ac with HVA, the only difference is this 3-hydroxy and this 3-O-methyl. So to get the 3-O-methyl from the 3-hydroxy, just add some COMT in there, catechol methyltransferase, COMT, and you get HVA. So summary of the metabolism again. You can have 2 pathways, MAO and catechol-methyltransferase. So MAO converts a dopamine into an alcohol and an acid. First by converting it into an aldehyde. Then this acid is converted to HVA, catechol-methyltransferase. So your final product basically is HVA. Let's see. Next, you can convert dopamine into 3-methoxytyrene by catechol-methyltransferase, which adds an O-methyl group, which transfers an O-methyl group, hence the name, on the 3 position. Hence 3-methoxytyrene. This 3-methoxytyrene undergoes MAO to form the acid. Instead of the alcohol, it forms the acid by an intermediate called the intermediate aldehyde called MOP-Al. So in both reactions, you form an aldehyde. Both pathways also utilize MAO. However, in the final catechol-methyltransferase pathway, MAO does not form the alcohol, it forms the acid. Oh, and MAO utilizes also COMT to form the acid. So both pathways utilize each other. It's just MAO and then COMT. And then if you use the COMT pathway, you're going to use MAO to get to HVA. Remember, alcohol dehydrogenase forms alcohols. Aldehyde dehydrogenase forms acids. Cool. So how do we fix dopamine levels in Parkinson's patients? You can increase synthesis of dopamine. You can stimulate dopamine's release at presynaptic sites. You can directly stimulate dopamine receptors. You can decrease reuptake of dopamine. Or you can decrease catabolism of dopamine. Hopefully things you should have learned in the psych module. So L-DOPA therapy. So if you remember that L-DOPA is a precursor. L-DOPA. Oh, I didn't even label that. So this little thing right here is L-DOPA. My bad, y'all. So this is L-DOPA. So if you remember that L-DOPA is a precursor to dopamine in the biosynthesis pathway. So what you can do to increase dopamine levels is by shooting up someone with some straight up L-DOPA to get them straight up dopamine. However, you can't shoot them up with dopamine because dopamine actually cannot penetrate the blood-brain barrier while L-DOPA can. This is because L-DOPA has a transporter while dopamine does not. However, the problem with inserting L-DOPA into someone is that L-DOPA can actually be decarboxylated. Because if you remember, L-DOPA can be decarboxylated. So what you can do is add some carbidopa. Not decarboxylated, it can be metabolized. So the problem with putting dopamine L-DOPA in someone is that L-DOPA can still be metabolized because it's a precursor to dopamine. You can still have metabolism of L-DOPA because it follows the same metabolism pathway as dopamine. So to get around the problem of the metabolism of L-DOPA, you add carbidopa, which inhibits peripheral decarboxylase, therefore increasing the amount of L-DOPA in the periphery. And by increasing the amount of DOPA in the periphery, by inhibiting its decarboxylation or its metabolism, L-DOPA migrates to the blood-brain barrier and acts on Parkinson's disease patients' CNS. However, it's important to note that carbidopa itself does not penetrate the blood-brain barrier itself. You can also have dopamine receptor agonists, like I said earlier, which include apomorphine and bromocriptine. These two are non-selective dopamine receptor agonists, meaning they also act on serotonin and alpha-adrenergic receptors. However, bromocriptine is more selective at the dopamine level. It acts as a D1 partial agonist, and it also acts as a D2 full agonist. Apomorphine is not selective for any of the dopamine receptor subtypes. However, they are both agonists. The more selective agents are rapinol, I don't know how to pronounce it. Pramipexole and rotigotine. Propanol is a D2 agonist, which also binds at D3 and D4 subtypes. Pramipexole is a D2 and D3 agonist, and rotigotine is a non-selective dopamine receptor agonist, meaning it can act on all these different subtypes. These contrast with your apomorphine and bromocriptine here because propanol, pramipexole, and rotigotine have low selectivity or low binding to serotonin and alpha-adrenergic receptors. So while apomorphine and bromocriptine can act on serotonin and alpha-adrenergic receptors, propanol, pramipexole, and rotigotine act less on the serotonin and alpha-adrenergic receptors and more on dopamine receptors, therefore leading to less side effects. Cool fact, so rotigotine was actually developed by a professor at VCU. If you ever went to VCU and took his orgo class, like I did, Dr. Midaskanyan, he actually developed rotigotine back in the day, which is the generic name for Nupro. So yeah, cool class, amazing professor. He's actually a really good professor. Let's see. If you get this, kick up and attack. Oh, that's what he used to say. Kick up and attack. So your MAO B inhibitors, so you can increase dopamine levels by inhibiting its metabolism, namely by inhibiting MAO-B and by catechol-methyltransferase. So you can inhibit MAO-B through selegiline and rasagiline. The main groups that are involved in this are the triple bonds here. So it's an MAO-B inhibitor by the presence of triple bonds here, which are called propargylamines, moieties, and these actually form covalent bonds with the cofactor of the enzyme. So MAO actually has a cofactor to enable the metabolism of dopamine. So what these do is they bind to the cofactor and not to MAO-B itself. So look out for the triple bond, that's how you know it's an MAO-B inhibitor. Sulfonamide is actually an MAO-B inhibitor, but actually does not have the triple bond. So it's still an MAO-B inhibitor, it's just, unlike selegiline and rasagiline, it does not have the propargylamine or the triple bond moiety. Next up, you have your catechol-methyltransferase inhibitors, tolcapone and talcapone. Two ways to remember this. If you know your Spanish, you know that poner, it means to put. So catechol-methyltransferase puts or poners O-methyltransferase. And you have pone, which is the conjugation for poner. Another way to do it is you got a pony named Comte. So you got your pony over here, your pony. Where is the laser? You got your, there it is. Pony named Comte or poner. So that's it. Thank God. Time to review. Remember, 5Dex Fest, Saturday, October 13th at 6 p.m. Lots of fun, lots of stuff, lots of food. Okay, so multiple sclerosis is caused by an infiltration of reactive T cells into the CNS, which damages myelin sheaths. There's two types of interferon, which acts as inflammatory and improves blood-brain barrier integrity to resist T cell infiltration. There's interferon beta 1A and 1B. 1A is glycosylated and has the same amino acid sequence as endogenous interferon, whereas 1B is the opposite, specifically as deletion of methionine 1. Your monoclonal antibodies, they bind to alpha-4B1 integrin expressed by inflammatory cells to block the invasion of immune cells into the CNS. Alemtuzumab and daclizumab bind to lymphocytes, and rituximab and ocrelizumab bind to B cells. Specifically, alemtuzumab binds to surface antigen CD52, daclizumab binds to interleukin-2 receptor CD25, and rituximab and ocrelizumab both bind to surface antigen CD20. Glatiramer is composed of, it's in the name, glutamate, lysine, alanine, and tyrosine. And just like vaccines, they induce tolerance of the CNS to immune responses, and they act as decoy for these immune cells to target them rather than myelin sheaths. Mitoxantrone acts as a type 2 topoisomerase inhibitor through the hydroxyl group arms, therefore disrupting DNA synthesis and repair. Specifically, they intercalate or alkylate DNA purine bases. Dimethylfumarate depletes glutathione and causes further induction of anti-inflammatory stress protein HO1. Fingolimod looks like sphingosine, and it acts as a sphingosine 1 phosphate receptor modulator. At the receptor level, it acts as a GPCR agonist, but because it activates the sphingosine 1 phosphate receptor. However, functionally, it acts as an antagonist by blocking the effect of immune cells on degrading the myelin sheaths. Specifically, it migrates lymphocytes into lymph nodes and prevents them from the autoimmune response in the CNS. Let's see. Teriflunomide inhibits pyrimidine synthesis by inhibiting dihydroorotate, therefore inhibiting T cell growth. Your skeletal muscle relaxants include mefenacin, which is your prototypical glycerol derivative. Remember your glycerols, this one has just straight up 3C carbon hydroxyl groups, whereas chlorphenicin, methylcarbamol, and carosorpidol don't have straight up 3 carbon hydroxyl groups. They have 1 carbamate group, which is an O, double bond O, and H2 at the top. These are more selective for the spinal cord and produce less sedation effects. Y'all know your benzos. GABA receptor agonists include baclofen, which looks like GABA. Remember, GABA is a gamma amino butyric acid. So you have your amino group and your acid group. So look for your amino group and your acid group, and you have baclofen. High dantoin derivatives include dantrolene, so both have the dan root in it. This binds to calcium channel proteins to regulate membrane potentials, which is disrupted when myelin sheaths are broken down. Also, now Alzheimer's disease caused by disruption of acetylcholine. Therefore, you can add acetylcholine esterase inhibitors. Or is caused by disruption in NMDA. Therefore, you add some NMDA antagonists. Your acetylcholine esterase inhibitors include tacrine, donepezil, rivastigmine. Tacrine is a type 1 inhibitor, meaning it sits on the binding site. Rivastigmine is a type 2 inhibitor, meaning it forms covalent bonds with the active site. Donepezil binds to the allosteric site. Galantamine is a natural acetylcholine esterase inhibitor, and it's a competitive and reversible inhibitor. NMDA receptor antagonist includes memantine. Your herbs and natural products. It's also thought that Alzheimer's is caused by disruption in tau proteins. And when you phosphorylate tau proteins, they detach from the microtubules and they self-aggregate, leading to plaques and neuronal death. Amyloid beta is formed by the cutting of APP amyloid precursor proteins by beta secretase and gamma secretase. And by forming amyloid beta, it actually aggregates or oligomerizes and forms plaques, therefore leading to neuronal death. Hence, your drug targets include beta secretase, which include BACE, BACE, and mimapsin, 2, gamma secretase, and alpha and amyloid beta itself. You can target amyloid beta by removing them, inhibiting its aggregation or oligomerization, or degrading it. Your diagnostic agents include Pittsburgh compound B, fluorbetabir, and fluorbetabin. If you see your isotopes, which are numbers in front of your carbons, your fluorines, then you have your diagnostic agents. Here's Cosette, and here's Wiley's Snapchat handle if you want to follow her. Feel free to give me any shoutouts if you have any of yourself, significant other, or your pets. I also accept good news if you want me to announce any good news, like if you're getting married or whatever. I also take good news if you want a shout out. Parkinson's, because everyone needs good news once in a while. Parkinson's disease is caused by deficiency in striatal dopamine. Your dopamine biosynthesis, first, you hydroxylate it, then you decarboxylate it. L-dopa is formed in the process, which is a drug used in Parkinson's. Metabolism follows MAO and catechol methyltransferase. If you use one enzyme, MAO, you're going to use the other, COMT. Or if you use COMT first, you're going to use MAO later. Let's see. Remember that the MAO pathway under COMT produces only the acid, not the alcohol, whereas the MAO pathway first produces both the alcohol and the acid. You can put some L-Dopa into someone because it's a precursor to dopamine, which works because dopamine has a transporter into the blood-brain barrier, while dopamine does not. However, dopamine can be metabolized or decarboxylated in the periphery. Therefore, you add some carbidopa, which inhibits decarboxylation in the periphery, therefore increasing the amount of L-Dopa, which migrates to the blood-brain barrier, and therefore exerts its effects. However, carbidopa does not penetrate the blood-brain barrier itself. Your dopamine receptor agonists include apomorphine and bromocriptine, which are non-selective neurons, which also act on 5-H serotonin and alpha-adrenergic systems. However, bromocriptine is more selective for the dopamine system in that it acts as a D1 partial agonist and a D2 full agonist. They're more selective agents for neurotransmitters in that they don't really act on or have weak affinity to serotonin and the alpha-adrenergic systems. Ropinirole, pramipexole, and rotigotine. Ropinirole is a D2 agonist that also binds to D3 and D4. Pramipexole is a D2 and D3 agonist, and rotigotine is a non-selective dopamine agonist. Your MAO-B inhibitors have your triple bond, except for sulfonamide. This triple bond forms covalent bonds with a cofactor of MAO-B, not MAO-B itself. And finally, you have catechol methyltransferase inhibitors, including tocopone and entacapone. Remember, Bonaire or your pony name Compt. Well, that's it from me for this episode. If you have any feedback, comments, concerns, or any constructive feedback, feel free to leave it at polyiv.com/CHRISTIANRUY629. Yep, that's it. Have a good rest of your week. Good luck on the exam.